Today, I'm going to talk to you about the detailed design and optimization of your concept. You now know what it is that you're going to build. That's exciting. And you know more or less who it is you're building the prototype for. But I don't want you to think at this stage that the imaginative and creative part of the project is over and that now it becomes boring, it becomes routine, and you have to be dutiful and come up with the obvious design and then build it. Because if you stop thinking creatively at this stage, and if you stop comparing different options and thinking about more unusual materials, more unusual ways of reusing components from scrap equipment, that kind of thing, then you'll find that you will come up with a very conventional and possibly boring solution at the end. Now, to give you an example, a few years back, I was working in a research group where they were looking at a way to move mirrors on satellites. And they were thinking of something like this. This is a stepper motor with a gearbox attached to it and some limit switches at the ends of the mirror's travel, and you can send a number of pulses to the stepper motor and it will step around to give a precise change in the mirror's inclination. The problem with this kind of thing is it's heavy, it's expensive, it has several hundred components in it, and every kilogram of weight in space costs a fortune. And you've also got the problem that the lubricants, if the device is not completely sealed, will then evaporate in space. You won't have any lubricants anymore. So building something like this is possible, but not a very elegant solution. And what they eventually decided to try as part of the research was to take a piece of very flexible rubber and paint a conductive coating onto each side of it and apply a few thousand volts across this layer of rubbery material. And if they applied opposite voltages, then it would squeeze the material together. Then because the volume is conserved, it tends to get longer, the piece of rubber. Or if they applied the same voltage to both sides, it would tend to repel, pull the material apart, and it would contract, it would get shorter. And this, if you like, was a form of electrical muscle. And they then mounted a mirror on some of these muscles to move a mirror for a prototype spacecraft. I'm not sure if they ever did it in space or not, but essentially it was something which did very much the same thing, but with two components instead of several hundred. And this is where it's important to think creatively, to think laterally, to have new ideas which are maybe a little bit crazy. So you now know what you're going to build, but I'll show you a few more examples. Here, for example, are two staplers. This one here is quite old. It's made of cast iron. It's designed for putting staples into things like the walls of buildings and notice boards, and designed for attaching things like maybe wire netting or cloth for fly protection, that kind of thing. And this is a standard office stapler, which is used for maybe stapling 10 sheets of paper at a time. And this is made primarily out of ABS plastic, the top parts, and polyethylene for the bottom. And they're very different. Not only do they do slightly different things. I mean, you can't really staple paper together with this, but you could put it down on the table and then thump the nail on the top and stick a staple into the table. Fortunately, there isn't a staple in there. And this one here is designed to staple together several sheets of paper. Very different weight. This is probably 5 times heavier than this one. It's probably also 5 times older, much more durable, but still something that's considered a stapler. And this is a bog standard office stapler. So this is the kind of stage you're at. In the context of this example, you could say, well, we're at the stapler stage where we know we're going to build a stapler, but we don't know what kind. We don't know what materials. We don't know where these materials are going to come from, or even how many components we're going to have. So at this stage, you want to be thinking quite carefully about the assignments that you did maybe 4 or 5 weeks ago, and when you were looking at the market, and think about what's important in this particular country. You may not have a final document describing the market that you are making this product for yet, because you'll have done this market assignment individually, and my recommendation would be that this week one person takes the market and then edits these market assignments from all of you, and maybe takes some of the best ideas from each of them, does a bit more research into one particular country and community within that country, and comes up with a final description of maybe 200 words in length describing the market. Because then you can come back to this market document and you can say, well, what's available in terms of skills and materials there? And what's maybe too expensive or too scarce or too complex, too difficult to understand for the particular market. So what you should be doing to begin with is thinking about where the main components are going to come from. So what are the main components going to be? How many components do you need? And how many of them can be made from recycled materials? How many of them can be taken directly from another product and then screwed or bolted onto your prototype without really having to modify them at all? An example of that might be the fan that you could take from a car engine, for example. Most car radiator fans are now powered by an electric motor. You could probably take the whole fan, the support framework, the motor, and then put it directly into your prototype. I've got a sheet on the topic of optimization, which I'll upload. I'll go through the main points on here. The first 3 points, the number of features, the number of parts, and the number and type of joints, concern the complexity of the product. How many features do you really need? Sometimes you might think, well, it's good to have a product that does everything. That often means, though, that it does a lot of things badly. And it's a little bit like a pocket knife, where your pocket knife has maybe 20 different functions, but actually if you just want a knife for carving wood, there's a better one. Or if you just want a pair of pliers for bending wire, there's a better pair of pliers. This kind of thing. So be careful about deciding to have too many features. Try to reduce the number of parts as much as you can, because parts are money. You know, every part has to be manufactured and assembled and possibly bought and sold and things, and the more parts you have, the more you're going to spend on your prototype. The next one, the number of joints. So which parts of the prototype are you going to build together out of a single piece of material? And which parts are you going to build separately and then screw together or click together or glue together? And it's a compromise, because if you have many parts, then if something gets damaged, you can remove one of these parts and replace it. And you can also optimize the materials you use, because you can say, well, this part's in bending, it maybe needs to be made out of a metal to give it sufficient stiffness. You can think, on the other hand, maybe a cover over the top of something. This cover is quite lightweight. Maybe it could be made from fabric, or it could be made out of thin wood, that kind of thing. The strength is not so important as the fact that it just keeps the things underneath it dry and free from dust, that kind of thing. So joints enable you to use different materials, but they add to the cost. So every joint costs something to design and manufacture and assemble, and also they can come apart unintentionally. So if you look at a hammer, for example, if you look at some of the hammers from Estwing in the USA, these Estwing hammers are forged out of a single piece of steel, which means that a very common failure mode where the head comes loose and comes off the handle can no longer take place, because it's just made out of a single piece of material. On the other hand, if part of it does get bent or damaged, then you can't really replace it. You've just got to buy a new hammer. The choice of material. This is somewhere where it's important to think creatively as well, I'd like you to think of at least 3 different materials that you could use for each component, if you can. I'll upload a data book from my time as a student, and if you look about halfway through the data book, there are some charts with lines and circles and things drawn on them, in which attempt to compare the properties of materials. And you can look at things like stiffness versus cast, or strength versus cast, fracture toughness versus weight, this kind of thing. Now, if you're interested in systematic material selection, take a look at this and maybe try it for a few of the parts in your project where you're unsure of what the best material to use is. The person who's best known for this approach is Professor Michael Ashby. If you look for the engineering materials book Ashby and Jones, I think it's volume 1, you'll find some more information in there. The next one, different shapes. Now, the shapes that you use for the different components have a great deal of influence on the strength of the components and their weight and so on. If you think generally things that are loaded in bending, they need to have a large second moment of area. Things where there's a high stress, they should have rounded corners and gradual changes in section, because the actual stress field itself, if you think back to Newton's laws, it's impossible for the lines which represent the load paths as determined from the principal stresses to sharply change direction unless there's an external force applied, and it's impossible for them to sharply change in magnitude as well unless there's an external force applied. So if you then have a sudden step in the surface of your component when it's highly stressed, you're trying to get the stresses within the material to do this. They can't do this, and these load paths, they get bunched up at the corners, and you get high induced stresses which can cause damage. Modularization and standardization. The more you can use standard components, the better, because it will mean that your prototype is easier to build in a developing country, and it's also easier to repair if someone needs to replace a broken part. Coming back to the idea of the car fan, you could say pick a vehicle that's common in, say, Africa or South America or somewhere, and when you make this prototype, you could say, well, this particular fan comes from a Ford Focus or a Toyota Corolla from the year 2000 or something, and then people will know, well, I can replace this. And things like motors, you may be able to get from a car, you might be able to get it from a washing machine, that kind of thing. But make some notes about the sources of the components that you're going to use, the reused components, and then if you, at the end of the project, if you decide to publish any documentation, and in your final video and things, you can say, well, where the components can actually be obtained from in the developing country. Surface coatings. So what material needs a coating to protect it or to make it look good? And in this case, with the very practical things that we're developing for developing countries, I'd suggest the main thing here should be protection rather than appearance. If you can do both, great, but the focus should definitely be on functionality rather than looks. Now, it's better if you can avoid surface coatings if it's at all possible, because they cost money. It costs money to paint something or to powder coat something or to galvanize something, and these technologies may not necessarily be widely available in the countries where your prototype will be used, especially things like powder coating or galvanizing. Painting is quite simple. You can do it with a brush or an aerosol can or something, and that's a technology that's available just about everywhere. As is, for example, coating something with oil to prevent corrosion. If you coat it with something like linseed oil, the oil will then dry a bit like a paint as well. And the last one on the sheet, the ergonomics and aesthetics. Does it feel good to use? Is it satisfying? Does it look good? I must say, here on the sheet I've also missed out 2 more important points, which I've since thought of in the last couple of years since I prepared this sheet. The first one is scale. So how big should your prototype be? And this depends a lot on the dimensions of the place where it's going to be used, the sort of body size of who it's intended for. Is it intended for a child or a woman or a man? But also, the scale can have a big effect on how tough something is. If you're talking about inertial forces which arise through things like dropping or throwing something rolling over, falling, that kind of thing, then small things are much tougher. If you take a model car, for example, and you roll your model car down a hill, even if it's a remote controlled car with motors and radio equipment and things in it, chances are it will survive undamaged if it rolls down a hill. If you try the same thing with a full-size car, it's going to get destroyed. It's going to get beat up. There's going to be all kinds of different damage to it if it rolls down a hill. But on the other hand, if the full-size car drives over the little car, then the little car is going to be destroyed. So small things are very resistant to inertial forces, which arise from dropping, throwing, impact, that kind of thing. And bigger things are much more resistant to external forces. And the last one I'll mention is how easy is it to manufacture? Is it possible to manufacture using simple tools and basic skills? Or do you need a sophisticated factory? Will your prototype still work if it's made to a relatively low precision? If the parts are not very accurately manufactured? And if you have a design and it still works, even if things are fairly inaccurately manufactured and made out of simple materials and using basic skills, and it's made quickly, then it's a great design.